Hello folks, so in this video I want to talk about how I go about creating the explicit equation of a sequence when you see the first couple of terms. So let's just get a refresher of what this actually means. The explicit equation is just an equation that lets you get any term based purely on the term that you're looking for. And what does that mean? Well, what I mean is that the only info needed is the number of the term, or the term number, I suppose we call it. The term number. An example of this could be, so let's suppose our sequence is a sub n is equal to, 2n squared. And if I want to find the, 50th term, or let's say the 51st term, well, I actually have all the information I need. I know that I'm looking for n equals 51. So all I need to do is plug in a sub 51 is equal to 2 times 51 squared, and that's some big number. So it'll be easier to explain actually if we realize what is not an explicit equation. And a non-explicit equation of famous example could be the Fibonacci sequence. So again, that starts off 1, 1, 2, 3, 5, 8, 13. How does this work? Well, the way you get the 2 is by taking these two 1s and adding them together. You get 3 by adding in these two, 1 plus 2, and so on. So it's hard. I mean, there is a way, I believe, to actually get the nth term, but it's really, really hard. It's often easier to explain this sequence, the Fibonacci sequence, recursively we call it, meaning that the term that you're looking for is you can find it based on what came before it. With this explicit equation, I don't need to know what any of the other terms are. I just need to know the number that I'm looking for. Okay, so what I want to do now is just talk about some common patterns that you'll see. So I'll just scroll down here. Actually, let's just clear this. Okay, so I want to just talk about some common, let's do that out of the way, common patterns, I guess we could say. Oops. And so a couple of common patterns that you already know how to create an equation for based on, previous math courses are linear or exponential growth. So linear growth, and well, we know what that looks like because we spend so much time on it as freshmen in Algebra 1, or even in Algebra 2, we looked even further in depth to linear growth. But again, that's going to be in the form of some kind of mx plus b. Now with sequences, that would end up being, instead of x, it would be n. So I'll just cross off and change it to n. But yeah, m is the growth and b is the figure 0, or y-intercept. 2, again, we have exponential growth now. Exponential growth. And that would be, again, something of the form a times b to the x, except instead of x, now it's n, right? So I'm not going to go too far into those right now because we're going to talk about these separately in a later video. But what are some other patterns you see? Other common patterns you see are, something squared, or n cubed, or n to the fourth. I mean, n to the fourth is less common, but you'll see this, these patterns pretty often where you have just the n raised to some power. So an example of like the sequence a equals n squared, well, this sequence would be, again, 1, 2 squared would be 4, 3 squared would be 9, 4 squared would be 16, and so on. I guess the fourth final pattern for me, anyway, and when I say, again, quote unquote common, to me these are sequences that I'm kind of looking for if the obvious pattern if there's no obvious pattern. So I'll try to fit it, like, does the sequence fit into one of these kind of families, if you will? So the fourth one is factorial. This is pretty common, again, similar to how if I showed you this sequence covering up the n squared, if I just showed you 1, 4, 9, 16, you would kind of just recognize them as the perfect squares. With factorials, this one is not as common, but I mean, when I say not as common, I think not as many people recognize them instantly. But once you start playing with them and seeing them more and more, they do become kind of commonplace or easy to recognize. So again, 1 factorial is just, well, that's 1. 2 factorial is equal to 2 times 1. So it's 2. 3 factorial is 3 times 2 times 1, so that's equal to 6. 4 factorial, this will be the last one we do. Oops, let me scroll down a little bit. Is 4 times 3 times 2 times 1, and that's 24. Okay. So whenever I'm looking to create the equation of a sequence, I'm really looking for one of these. And of course, I guess the 5th one, which is kind of, it doesn't really fit into any of these, is variations of this. So for example, you might see something like this. I don't know. Oh, how about this? 2, 4, 8, and 26. And so clearly it doesn't fit exactly into any one of these 4 families at first, but you might recognize this as, like so. This is actually, oh, I'm sorry. This should be a 3. You might be able to see it like so, where this is actually just 1 plus 2. This is 2 plus 2. This is 6 plus 2. 26 is 24 plus 2. And so I notice, oh, wait a minute. These are just the factorials, and there's a plus 2 tacked onto the end of it. So really my sequence for the nth term, or my equation for the nth term, would simply be n factorial plus 2. This often also happens with fractions. So if you have a fraction, you can just break it up into 2 separate sequences, one for the numerator, one for the denominator. And we'll just make one up right now. How about my sequence is this? So I could have, I don't know, 3, sorry. We'll do 4 fractions here. We'll do 3, 12, 27, and then 48. And then in the denominator, we're going to do, let's say, okay, that took me a second to kind of just figure out a good one. But in the denominator, we're just going to have 2, 4, 6, 8. Alrighty? So again, if I want my equation for my sequence, I really don't care about the actual like overall value. Like I don't actually care that this is 1.5 or that this is equal to 3 or that this is equal to whatever that is, 4 point something. I can really just get the equation. It's actually probably going to be easier most of the time. I suppose not all the time, but yeah, most of the time, it's just easier to look at the numerator and denominator as 2 separate sequences. Okay, and it often helps also to create a table. So let's pretend that I don't see the obvious pattern here. If I look at the denominator, I have n and an a sub n. So the denominator for the first term, again, the first term corresponds to a sub 1, unless otherwise stated. The denominator is 2. In the second term, my denominator is 4. My third one, denominator is 6. And then 8. And so this one's pretty straightforward. These are all just the even numbers. And so this is really just 1 times 2. Actually, we're going to change the order there. Is 2 times 1. This, 4, is 2 times 2. 6 is 2 times 3. 4 is, 2 times 4. So you would probably guess that if we were to go on, the nth term, whatever it is, its denominator is simply going to be 2 times n. So that's what I'm going to put in my denominator here. Again, so these just end up being what I see. And then again, I really think the table does help when you're when your back's against the wall. This would be 2n down here. Okay, let's look at our numerator now. So again, for n and any given term, we'll go 1, 2, 3, 4. Our first numerator is 3, then 12, then 27, and then 48. Okay. So one thing I do notice is that these numerators are all divisible. Sorry, yeah, these numerators are all divisible by 3, and so you kind of like factor them out because that does help. So what I'll do is I'll write this as 3 times 1. Okay, this one will be 3 times 4, 3 times 9, 3 times 16. Okay, so now these probably do look familiar. You might notice this as the perfect squares. And so if you write our numerators, the nth numerator is simply going to have a numerator of 3 times n squared. And so I can put that right here. And it turns out we can actually, if we wanted to, we could simplify it. This equation says a sub n is equal to 3n over 2. Okay. But so it does definitely help that we wrote it out like this. But yeah. So those are just a couple of tips, and hopefully you grabbed some out of this video. Again, when I'm looking to create the equation of something like this, specifically it's a fraction, break it up into a numerator and denominator, and treat their sequences differently, or find their sequences differently, separately. And when I'm trying to look at an actual sequence on its own, try to kind of force it into, not force it, but see if you can break it down to contain one of these kind of 4 families. All right, so in this case, we did it by noticing, oh, it's just 3 times all the perfect squares. Or we saw up here where it's simply like the factorials, plus a constant, plus 2. So that's a couple of my kind of, I guess, tips and tricks, if you will. Hopefully this is helpful, and I'll catch you in the next video.